Okay, well, at this point in the course, we're finally going to start into transistors. So in this lecture, we're going to cover three types of transistors: JFETs, MESFETs, and HEMTs. We'll get to MOSFETs starting in the next lecture, but first we're going to cover some more conventional type field effect transistors. These are all field effect transistors, hence the FET part of that, including a HEMT as well. But we're going to cover these first because they're a little bit more diode-like in terms of how they're modulated compared to a MOSFET. And so that'll be a better progression as we move into field effect transistors. The image to get us started here is a field effect transistor. This is particularly a high electron mobility transistor, or HEMT. We'll talk about that at the end. And these tools, like you see here, are utilized to model devices and predict their behavior. So you can use the equations we use in class, but they don't really give you a picture of what's happening in the device. And so if you look at this, you've got your source, gate, and drain for the transistor. You've got some semiconductor layers. But importantly, this modeling software was able to plot electron concentration in the device while it's operating, so you can then optimize the device for maximum currents, reducing gate leakage current, things like that. And so these are based on numerical analysis, and these are the type of tools device designers use. But of course, if you want to do modeling software, you have to understand the basics we cover in this class, because then you wouldn't be able to know if this solution here made sense or not, right? Because sometimes numerical analysis can give you complete garbage. So you have to understand the fundamentals before you go and try to do numerical analysis modeling. At the end of this lecture, at the very end, we'll try to figure this one out. So I'll ask you to tell me what's happening in this actual diagram. But first, let's move on to our first topic. So, we're going to start out here with JFETs. And I want you to consider a JFET, which is this three-terminal device. Again, if it's a transistor, we've got three terminals, not two terminals like a diode. And if you look at this, I've got a source, a gate, and a drain. Now, a little bit about the terminology. The reason why we call this a source is that if you look at how I apply the voltages here, negative on here, positive on the drain, the source, because I put positive voltage here, acts as a source for electrons. So you could see how electrons could be flowing from the source to the drain. And so you could think of the source as being like a spring of water out of the ground, hence ground here, right? And the drain would be basically where that water drains out, the water being electrons. So that kind of helps me remember the difference between source and drain. I also have gate electrodes. I've got gate electrodes on both sides here, which is important. And so I'm obviously turning this device off through application of voltage here and here. And again, if I apply a voltage between the drain and the source electrodes, I will get current flow. So put positive voltage here, I get electrons going like this, which is current flow in this direction. Okay? So, let's say I've got this all set up, I've got current flow from source to drain, and I apply a negative voltage to my gates. Well, what will happen? Well, what you would expect to happen is this is a PN junction, right? And so if this is a PN junction, that will reverse bias the PN junction. When you reverse bias these PN junctions with negative voltage here, with respect to here and here, the depletion region grows, and as the depletion region grows, this conductive channel could disappear. So I could then use gate voltage to modulate the current flow through the channel, basically achieving transistor action, because it doesn't take a whole lot of current or voltage to modulate a large change in current flow through the channels. If you look at this, the doping levels have been selected very carefully. I've got P plus and N. Why do I have it set up P plus N and P plus, where the gates are P plus? Well, again, it comes back to that depletion. I want the depletion to occur only where it's going to do something for me, right? And the only place where this is going to do something for me is to deplete into this channel here, into this N-type channel. And so this is lightly doped, this is heavily doped. All the depletion will occur where I want it, which is into the N-type channel, and the device works as I would hope it would. So I'm showing you what happens here. You apply a negative voltage to the gates here, okay? And you could see I deplete all this area. So I've depleted this channel, and then I get no more current flow from source to drain, or really from drain to source, which is electrons from source to drain. It's gone because I've depleted this out. And again, a key thing to note is it did not take much current to reverse bias the PN junctions. The current required at the gate here is I0, reverse saturation current, which is extremely small. It's not zero, but it's very small. And so again, I have a transistor or amplifier which requires very little input current and a little bit of voltage to modulate a significant amount of output current through this device. So I get amplification using what is called a junction field effect transistor. It's based on junctions. Because the current's so low, it's basically primarily based on voltage that modulates this. So it's a field effect, electric field type effect, and it is a transistor, hence the term JFET. So let's start to analyze this in terms of the current capability, and we typically only need to focus on the channel region. So I've taken the diagram on the previous page, and I've simplified the source and drains, which were off to the sides, and I'm just looking at the conductive channel between the gates, because that's where all the modulation is going to happen. Okay? And so if you look at this, what kind of current would you get, and what would the IV look like? Well, that's pretty easy. This is just resistive semiconductor, right? And so if I look at my current versus voltage, it would look like a linear response of I equals V over R, right? Furthermore, because this is a uniform resistor across here, this is my positive drain voltage applied here. You can see that as I move in positive distance x across here, my voltage increases in this direction. So basically at this side I know I've got VD, okay, so it goes to VD equals E, which is my potential applied here, on this side. On this side I know it's ground, obviously, and in between I've got a linear drop of voltage because this is just a uniform resistor. That's going to be important in a second. Okay? So, this type of relationship where I can assume that the voltage linearly drops and it just acts like a resistor is only valid for very low current levels. The thing I want you to figure out is what will happen at higher current levels, where I'm putting more and more voltage here. And here's a hint. Again, this resistor has a voltage drop across it. So as I increase this voltage increases here. And so look at what happened. Look what might happen here. I'm putting more and more voltage here. Okay? Positive voltage here. Let's say I've grounded my gates or something like that. What's going to happen to this PN junction here? Well, if you can answer that, you've done a great job. On the next slide here, which explains exactly what happens. So, here's my JFET. For low voltages here, to start out, my drain current versus drain voltage response is approximately linear, because this is just acting like a resistor. As I further increase my drain voltage, what you'll start to see is that I get a higher voltage here, and a higher voltage drop across this channel. If this is positive voltage on the N side of a PN junction, then it is reverse biasing that PN junction. See how I have the gate and the source grounded here? And so positive voltage on the N side is reverse bias for a PN junction. So you can see I'm reverse biasing this. And of course the voltage drop decreases as they go across this channel, and so the reverse bias amount decreases as well. In fact, down here I've got no reverse bias because both of these terminals right here are connected to ground. Okay? And so at this point, my channel is decreasing in conductive area, and so my current starts to saturate. It started as linear, and now it's starting to roll off a little bit. If I keep going, eventually I have enough drain voltage to fully reverse bias the PN junction right here at the input to the channel. And I get something called pinch off, which leads to saturated drain current, meaning that if I keep increasing this further and further with drain voltage, I get no more current increase. Okay? And this pinch off it's pretty interesting. So, some of you might look at this at first and be like, well, I would expect that as soon as this thing pinches off, that if I put more voltage here, the current should disappear, right? Because if I totally block this channel, the current should go down. No, it stays as a constant level, and here's why. Okay? Think about it this way, okay? Let's say I get enough positive voltage to reverse bias this PN junction to basically deplete it all the way here. As soon as I've done that, you could say, okay, I have no current flow through here. Well, wait a second. As soon as I have no current flow through here, then my voltage of 0 volts should basically be reset across here. I have no voltage drop, no current across the resistor, no voltage drop, and so I should get back to 0 voltage here. Well, if I have 0 volts here, right, then I have no reverse bias across this PN junction, so then it opens back up. So then you could say, okay, it opens back up, but then the voltage starts to appear in the channel again, shuts itself off. If it's shut off, then that 0 volts gets back in here because there's no current and no voltage drop, and then it opens back up again. And so you'd have this balance of basically it trying to shut itself off, but it never can, because if it ever shut itself fully off, it would basically find itself in the non-shut off case because you would have 0 volts here and no reverse bias. And if you looked at this even more closely, you would find that even if you have a barrier here, it could be so small at this very end that you could get tunneling of carriers through it. So the key point is that eventually I get to a point where the channel is pinched off, hence the term pinch off. See how the channel is pinched off here? And at that point the current saturates, meaning it stays constant as I increase my drain voltage. Now, one way to counteract this is if we're out here beyond pinch off and in saturation, is we can actually put a gate voltage on here to modulate this, okay? And so how you would typically operate one of these transistors, okay, is that you would take it out into the point where you're in saturation. You take it out to the point where you're out in saturation. So here's my drain current versus drain voltage. Here's a curve for VG equals 0. Here's pinch off. Here's saturation. And what I will do is I will further reduce the amount of current that I get by putting a more negative gate voltage here. So if I put a negative voltage on the gate, that reverse biases this further and would further reduce the conductivity of my channel, right? And so I would further, more negative voltage would further reduce the conductivity through my channel. And you can see that here, again, each of these curves is for a different gate voltage, and you're reducing the current. So I can use an input voltage to modulate an output current. This is a type of transistor which is normally on, meaning if you don't apply a voltage at the gate, it has current flow, and you have to apply a voltage to turn it off. Okay? And you can see here's the pinch off voltages at which all of these start to level off and saturate. Here's a question for you. Okay? If I reverse the dopings, how would all of this change? So if I reverse the P and N type dopings. Well, that's simple. You would have the exact same curve here, except that you would have positive voltage because it would be an N plus P junction. You need opposite polarity voltages to reverse bias it. You could still have the same drain to source voltage and current direction because this is just a resistor, and a resistor doesn't care if it's P-type or N-type material. Okay? Now, a great simulation could be found at this link here. I know you can't click on a link in the video. You could go to the PowerPoint file and click on this, or just Google JFET CAM UK. I encourage you to open up that simulator, and it shows the carriers moving through the JFET as you modulate voltages on the drain and the gate. So give it a quick try. It really helps show how the device operates. So now let's actually get some equations to predict current flow through this device. And this won't be too bad, so let's go through a derivation to figure this out. And so obviously we know that the amount of current flow through this device will be dependent on depletion region thickness, the width of the depletion region, right? And so we'll start there. And we know that for a PN junction, the width of the depletion region can be calculated as follows. We also know that this term here is just the contact potential, so I can simplify it down. And we know that depletion region width, if I reverse bias it, can be calculated as follows. And remember, reverse bias is a negative voltage, so negative makes it a positive, so it's V0 plus some reverse bias number. And that makes sense because more reverse bias, this gets bigger, and then depletion width increases as well. Okay? So let's start to look at some of the terms here, okay? And simplify this down further. So this is a P plus N junction, right? So we know for the case of P plus N that I can get rid of the Na term, okay? The other thing is typically I can assume that I'm putting enough of a reverse bias on this that it's going to be much greater than V naught, so I will basically replace this whole term with just the applied voltage, which is VGD, the voltage applied between the gate and the drain, because that's the end of the channel that's going to matter the most to achieve pinch-off, between the gate voltage, which comes out here, and the drain voltage right here, which determines the amount of pinch-off. So, my depletion region width at pinch-off is equal to this here, where I simplified it down, VGD, and it's just ND because it's P plus N. Okay? Okay, introduce some more terms here. At the point of pinch-off, my depletion region width will equal A, which is half the channel width. So obviously if I want to deplete the whole channel and pinch it off completely, it needs to go all the way to this distance A, which is half the channel width. And so what we'll do is we'll substitute in W equals A, solve for it as follows in terms of pinch-off voltage, and we'll introduce we'll introduce the pinch-off voltage as well for VGD, saying that pinch-off voltage is the point where VGD is enough to cause this to pinch off like we saw in the previous slides. I'll solve for VP and I get the following equation, which now predicts pinch-off voltage for a JFET. Remember, that's the point at which the current will saturate, even if you increase ND. And that makes sense because look at this equation. VD does not appear in here, meaning that once you get to the pinch-off voltage, you're done. The other thing that's interesting is that this is only dependent on ND. Why is that? Well, that's one of the assumptions we made. We said that all the depletion region width is into the N-type material, not the heavily doped P-type. And so that's why the pinch-off voltage is only dependent on ND. Okay, so now we're getting closer to derive the current, and to do that we need to basically calculate the resistivity of this channel. Resistivity is easy to calculate. Resistance is resistivity, rho, times L over A. So rho L over A, and A is the thickness and the width of this, okay? And so what we're going to do is we're going to set up a differential resistance, because if you look at this resistor, this is not a uniform resistor, right? It's less resistive here and more resistive here because it's more constricted. And so what we're going to do is for L, we're going to substitute dx. So my length for a standard resistor would be 0 to L, right? Going from 0 to L. But this resistance changes as I move across here, so I'll try to get the resistance at different intervals dx. So I will substitute dx for L, meaning so I can look at the differential resistance as I move across the channel from 0 to L. The other thing I'm going to do is my thickness. So if this is my length and this was my thickness I'm going to substitute as being 2h of x. So h is basically, you can see this, h is A minus W. It's how much of the channel on this side is undepleted. And the total is 2h. So if this is how much is undepleted on this side, this is on this side, 2h is the total width of the undepleted channel. Again, you can see how that changes as I move across the channel. And so that is also a function of x. I'll put these in there. I get a differential resistance, which is rho, now dx over z, which is the width in this direction. So it means into the plane here. Okay, so what's the in and out of the plane here? How deep is this device? And then the last thing I got is 2h of x, which is the dimension in this direction. Okay? So then it's easy. If I have resistance, I can get current. Well, current is voltage divided by resistance, and that's all I'm doing here. Except that for my voltage, it also changes as I move distance, so I have dVx. You can see my voltage drop as I move from the left side where it's VD to the right side where it's 0, because it's grounded, changes, and so I have dV sub x here. Okay? So now I've got everything, and you'll notice that this is actually easy to solve. This is a differential equation, but it's a first order one. These are the easiest types to solve. And so let's just do that on the next slide. So let's get ready to set this thing up for solving it, and let's move some terms around. We already know that we already have pinch-off voltage. We know that our voltage on the gate at any position here, VG sub x, okay, as I move across here, is the gate voltage minus the voltage V sub x here, okay. I know that my width, I have this from the previous slide, my width at any point here from my depletion region, okay, is dependent on the voltage between the gate and position x, VG sub x, and so that changes across here as well, hence the sub x part of this. And I know my half width of the channel, H, is just A minus W. So I have all those. If I use all these terms and I reorder them, I can solve for H of x as follows, being equal to A, which is the half channel width, it's the half channel width. And these terms dependent on V sub x, the voltage at various positions across here, V sub x, minus V sub g divided by the pinch-off voltage. Okay, I'm going to substitute this new H of x into my simple equation for the output current. That makes sense because I have all these other terms, but I didn't have this term H of x. That's why we solve for it. So I substitute this in there. I'll take my dx to the other side, and then I have I dx equal to all this stuff, now that H is in there, dvx. And so what you can see, this is a simple first order differential equation. If I integrate both sides, I could then get the solution for this. But the question is, over what limits should I integrate this? Well, it's easy. Just look at your device, okay? They just apply common sense. My distance dx obviously is going to go from this side, which is 0 to L on this side. So I'll go from 0 to L. So I'll integrate on this side from 0 to L. And on this side, my voltage goes from 0, right? It goes from 0 to VD, right? And so I'll integrate this side from 0 to VD. If I do that, I won't force you to go through the integration. You'll get this following solution for the drain current times ID times L. I'll move L back to the other side, and I'll end up with the following equation, which is accurate for my drain current through this device at low current levels. This term G naught, I just basically grouped the terms A, Z, rho, and L all into G naught. Remember, Z is the depth of this device into the plane here, so how sort of wide is it? L is the length of my channel, rho is the resistivity of the N-type semiconductor, A is my half channel width. And this, if you look at this, this is just 1 over resistance, right? It's the exact opposite of rho L over A. It's 1 over that, essentially, and it's basically referred to as my conductance for the channel. Hence why we use the term G naught. So, you have G naught out front, and then you've got all these other terms that are a function of pinch-off voltage, drain voltage, and gate voltage. I know this equation looks a little bit messy, but you know, when you think about all the things going on in a device, semiconductor device, not too bad if you can get the drain current as a function of these simple parameters like this. Okay, so again, we said the previous equation was for low current levels, meaning that I'm out here where I have sort of a linear response, okay? What happens when I get to the point where this thing pinches off and starts to saturate with the current? Well, if we keep increasing our drain current, we run into pinch off, and this term here goes to unity. Because when I get to pinch off, VD minus VG is the pinch off voltage. When this thing, essentially when this depletes all the way here, I'm at pinch off voltage, and of course VD minus VG equals VP. So I'll substitute that into the previous equation here. This term becomes 1, and so I end up with just minus the 2/3 here, essentially. Okay? And then I want to basically simplify this a little bit further. Let's see if we can get rid of the drain voltage here. Okay? And we'll talk about why we did that in the end. And so if I look at this, getting rid of this term here, I know my pinch-off voltage is equal to VD minus VG, right? That's the voltage at which I pinch off the channel, is obviously the point where VD and VG have the difference to do so. So I'll divide both sides of this equation by I'll reorder this and divide both sides by VP. I will then notice that this here, these are the same, so I'll put in here this 1 plus VG over VP, put it in here, and I get the following equation here. The equation says as follows: my saturation current is equal to that channel conductance times a bunch of terms which are dependent on pinch-off voltage and gate voltage. Again, this is my saturated drain current, and there's no drain voltage term. Does that make sense to you? It should. That should make complete sense to you. Because look at our curves here. When we are in saturation, the current is no longer affected by the amount of drain voltage. You're in saturation. That's the definition of saturation for a transistor. And so I would expect that my calculation for saturation current would have no VD term in it. It's only dependent on the pinch-off voltage and the gate voltage, because of course if I change the gate voltage, I could reduce my saturation current. So now we've got an equation to predict that for the JFET. So once we've got our saturation current, and that's how we typically like to operate a JFET, is out here in saturation and just modulate the gate voltage. We can then develop a simple circuit model for this, which is really simple. Okay? So what I want to do is basically notice that I have, for this device, I modulate an input voltage, VG, which results in a change in output current. Well, that means transconductance, right? We talked about that before, right? Transconductance, you take an input voltage and it modulates the output current. So GM has units of amps per volt, right? And so if I multiply this times volts, I just get the amps. That's how transconductance works. So how do I solve for transconductance for this? Well, again, if it is the change in output current as I change in input voltage, then I will just take the derivative of output current, ID sat, put this in here, with respect to the input voltage. And that makes sense too. Here's my units for transconductance, amps per volt. So I take the derivative of all of this with respect to gate voltage, and I get the following equation here, which gives me my transconductance. And if I want to put this in a simple circuit, I could do it as follows. Here's my input voltage, here's the transconductance, I put it in here, and it gives me an output current as a result, which I can have across my load. Okay? Again, you're transferring an input voltage to an output current. There's the trans part of transconductance, and it's conductance because the units for GM are amps per volts, which is the opposite of resistance. It's conductance. I want to emphasize that transconductance can be for just about anything that gives you a transconductance. So let's say you went to an apple orchard, you picked an apple from a tree, and you found it has transconductance, then you could represent it this way. Now, I know an apple doesn't have transconductance, but I'm just saying any black box device that you change input current and it gives you a change in output current, you could represent with a simple circuit transconductance as follows, and that's why we like transconductance in electronic circuits. Now, let's say you're a JFET designer and you want to make the best possible JFET. Well, you want to have a high transconductance, right? But you can't cheat, meaning that obviously if I could get a more and more output current, right? More output current would give me higher transconductance, right? More amps for a given volts would give me a higher output current. So if you look at the JFET, you'd say, well, okay, if I want to win a transconductance design contest, I'm just going to make this device thicker, meaning that my depth into the plane here for this device would be really wide. So let me try to draw this here. I could have a JFET that would be, like this, where here's my current flow going through it, but if I wanted to win this contest of transconductance, I'd say, well, I'm just going to make this JFET even deeper in this dimension here, right, which is the dimension into the board here. So I've got less resistance here, and I get more current to the device. Well, to be fair, when people measure figure of merit for a JFET, they say, how good's your transconductance? divided by how wide is your depth Z. So here's Z here, here's Z here. If you make Z bigger and bigger, sure, your transconductance will go up proportionally, but this basically accounts for that because then you have to divide by Z. And so that's your figure of merit for a JFET. Lastly, it can be shown experimentally, meaning that you can't derive this theoretically, but you can get a pretty good approximation for your saturation current out here as being IDSS over times 1 plus VG over VP squared. Okay, this assumes that the gate voltage is reverse biased just a little bit at least, where this IDSS is the saturated drain current with VG equals 0, which can be calculated as follows, just a simple equation. So not bad. At the end, you can just use this equation, which gives you, here's your term you put out here in front, and then there's your voltage terms there with the gate voltage applied there. Let's look at some examples. Here's a commercial part you could purchase. This is a low-frequency general-purpose amplifier. It's a JFET in this package here. And again, JFETs are used when you need a high output current, because this is a pretty conductive channel, with a very low input current at the gate. Okay? Think of a BJT. Sometimes you might have too much input current. Think of your input current for a JFET. It's really, really low, because this is a reverse bias diode, right? And so you have even less input current. And sometimes, if you have a MOSFET, you might not get enough output current. So that's kind of a sweet spot in which JFETs can operate. Here's the, off the spec sheet, here's the drain current versus drain to source voltage versus a couple gate to source voltages applied here. We can calculate the transconductance. I have a load line plot here as well to help me out that I took from the spec sheet. Let's say I change my voltage from 0.1 to 0.4 volts. So that's a difference of 0.3 volts. That's my change in gate voltage, dV. How much is my output current change? Well, based on the load line, the maximum it changes by is 1.8 to 0.3. That gives me milliamps over some kind of volts. If I calculate that, I get a transconductance of 5 times 10 to the minus 3 mhos, right? It's conductance, so it's not ohms, it's mhos. Let's look at a JFET in the practical applications used in an op-amp. So this is a wide bandwidth single JFET operational amplifier. And if you look at the features, it says something which is very attractive, high input impedance JFET input stage. What's that mean basically? Well, here's the inputs, right? So here's your inputs, here's your JFETs, okay? And the reason why this is attractive is if you look at a JFET and you look at the input at the gate, okay? So here's your voltage input. You know, first off, in terms of impedance, it's a reverse bias diode, right? And so it's like this resistance is very large, okay? That's good because that means your input signal here, okay? So whatever your input signal is that's coming in here, before it goes into your device, it won't take a lot of current to drive this, right? So it won't take a real powerful signal. The input for the JFET won't suck down the signal from your input line. And the other thing that's nice about a JFET is that the gate is a reverse biased diode, right? And so that means that my capacitance is also going to be low, right? If you reverse bias a diode, the depletion region increases. Well, that's perfect because if I look at impedance, okay, let me erase this here. If it lets me erase it. I always have trouble getting this to erase once I did it. Sorry, that's supposed to be a plus. Plus 1 over j omega c, right? This is my input impedance, which basically gives me the effect of my input impedance for a signal for both AC and DC signals. And so if I look at the DC portion of this, it's dominated by the resistor. High resistance, high input impedance, that's what I want. And if I have a small capacitance, this goes down, this term goes up, and also gives me a large input impedance. Hence why it says high input impedance JFET input stage. Perfect for an amplifier. Small signal in is all you need because you have a high input impedance. And here's a paper I found which is really amazing. This is a JFET and the capability is pretty remarkable. It is a 1700 volt, 54 amp JFET. Huge amount of power density. Okay? How did they achieve this? Well, first off, they use a wide bandgap semiconductor, meaning that it can really take the heat and it has a very high breakdown voltage. So they can do high voltage operation with this. And if you look at this, how they do it is they basically the gate only needs 1 milliamp per centimeter squared to achieve this high output current. Okay? And this high output current is over a very small active area. Again, because silicon carbide is a wide bandgap semiconductor that is really take the heat. It's a tough semiconductor. And so how do they design this thing? Well, the JFET current goes in this direction. So here's my source, here's my drain, okay? Or that is the electrons go in this direction. Here's my gates. And so what you have here is basically, this is like a donut here, that if they reverse bias these PN junctions, it will pinch off the channel here. So this P plus implant area, this gate here, is if you looked at it from the top, it would look like a donut essentially, and you would get all your current flow down through the center of that donut. And if you put more gate voltage, you would basically reduce the width or the diameter of this conductive channel here. So again, they said it can block when you turn this thing off. It can hold off 1700 volts roughly, using only minus 24 volts at the gates. Minus 24 volts makes sense. This is the P-type region, so you want negative voltage on the P to reverse bias it. And it can put out 54 amps roughly with a very little amount of input current. So you can see how you can make a very powerful amplifier, really high power, using a JFET. Okay, here's the review, and then you can take a break, and then we'll move on to some other topics. First question, this is called a transconductance operational amplifier. Look, I've got input voltages here, output current here. I just wanted you to tell me, for this op-amp, why do they call it a transconductance operational amplifier? That should be easy. Just look at this, and you should be able to figure that out. Here's my JFET. Easy question. Do I need positive or negative voltage to turn off the JFET? Next question, if I keep increasing the drain voltage, more and more drain voltage, does my current keep increasing more and more? And if not, then what's this called? There's two terms that I'm looking for. One describes the voltage at which it occurs, the other describes the current flow and what it's doing through the device. Next question, why is the JFET gate heavily doped? That's pretty easy. Think of the way you want to deplete this. Last question, what's a key advantage of using the JFET? Think about the best amplifiers, and they have a very high input impedance, and you should be able to get that answer out of these three. Okay? And that's